Design is not just what it looks like and feels like. Design is how it works. Hello everyone. Today we are going to derive the governing differential equation of a bar that is subjected to uniformly varying axial load. So let me represent a cantilever bar here. The reason why it is cantilever, it is fixed on the left extreme end. So it is built into the wall on the left hand side. So you can call it as a cantilever bar. You may call it as a beam, but for a beam the loading acts in the transverse direction. For a beam the load should act like this. But in our case the loading is not going to act like this. It will act along the transverse direction. Okay, let me first define the geometric properties of this bar. This bar has got a length of magnitude L. It has got a cross-sectional area of magnitude A. So these are the geometric properties. Let me define the material property. This bar is made up of material that has got an Young's modulus value of magnitude capital E. If the bar is made up of steel, you substitute the Young's modulus value of steel. If the bar is made of concrete, go ahead and substitute the Young's modulus value of concrete. So it is a material property depending on what material the bar is made of. Now comes the important thing, that is the stuff that is acting on this bar. Remember, the bar is not subjected to uniformly distributed load. It is subjected to uniformly varying axial load, which means the rate of loading gradually increases as you progress towards the right hand side. So I'm representing that very carefully here. You see that the arrow marks are increasing as you progress towards the right hand side, which means that the rate of loading is increasing gradually as you move towards the right hand side. Okay, now I'm going to represent this particular physical scenario mathematically. So once I have represented the physical scenario mathematically, then I will represent this particular physical scenario graphically. Then once I have represented the physical scenario graphically, then I will represent the physical scenario by giving an analogy so that you can easily relate and get an intuitive idea of what this physical scenario actually is. So here is the mathematical representation. The rate of loading is given by this expression Q into X. Now why would I say that? Because when X is equal to 0, there is no rate of loading. At X is equal to L, the rate of loading is highest. It just spikes. And the rate of loading increases in a linear fashion. And remember that the unit of Q into X is Newton per meter, or it may be Newton per mm, depending on whatever unit is conducive for you. All you want to remember is Q into X is the rate of loading. Remember, it is not Q that is the rate of loading. Q into X should be the rate of loading. Fine. Next, I'm going to represent this graphically. So here we go, graphical representation. So let me entail a set of coordinate axes. X-axis represents the arbitrary location on the bar. Y-axis represents the rate of loading, which is Q into X. So if you plot your graph, how do you think the graph is going to vary? The graph varies in a linear fashion, just like this. At X is equal to 0, the rate of loading is 0. At X is equal to L, let us say this is X is equal to L. The rate of loading spikes. This is at X is equal to L. This is at X is equal to 0. Now what I'm going to do is I'm going to consider a small strip. You know where we are heading. You know where the story is heading. But wait a minute. Let me consider a small strip. So I will use this yellow to consider a small strip just like this. Just like this. You know that we are going to integrate. But let me not, I'm not holding any suspense here, but Just wait and allow for the concept to sink in. And why we have to integrate? Let us find that by using a physical scenario. Okay, here we go. I'm going to represent the physical scenario, and let me try my best to represent the physical scenario, and let me get a point as interesting as possible. So let me move on to the next page, the physical scenario. So I'm going to draw four guys. The first guy, he is going to be the smallest one. His name is Alex. The next guy, he weighs heavier than Alex. Let us say that his name is J. And the third guy, he weighs even heavier than J. And give a name to him, we will call him John. And the fourth guy, he weighs even heavier than John. We will call him Peter. Okay, there is a ceiling. I'm going to represent the ceiling by this blue line here. I'm sorry, this is a green one. Okay, anyway. This is the ceiling. Okay, here we go. Now what I'm going to do is, Alex will hold on to the ceiling. He is clinging onto the ceiling. So let us take Alex. Okay, Alex, please come. Take Alex, and he is holding onto the ceiling. I don't know how he will hold onto the ceiling. If you want to imagine a rope of some sort, maybe something like this, a rope of some sort. Okay, so that is Alex clinging on to the ceiling. So that is Alex. The next person is J. So let us take J. J, we need you. So take J, and he is clinging on to the foot. He is holding on to the foot of Alex. So maybe a rope of some sort. It is more an exercise for your imagination than the intellect. So this is a terrible, terrible diagram. Put up with this diagram, please. Next person is John, and what John is doing, he is holding on to the foot of J. So take John. Oh, John is showing some resistance. John is reluctant. So, but anyway, John, please come along. And John is holding on to the foot of J. So this is J, and this is John. And the last person, our big guy here, that is Peter. So let us bring Peter. Okay, Peter is cooperating. Okay, Peter is holding on to the foot of John by a rope of some sort. Now if you compare this particular physical scenario with our physical scenario, this is like a bar that is subjected to uniformly varying axial load. This is like a bar that is subjected to uniformly varying axial load. So if you compare this particular physical scenario and you compare this particular physical scenario, both the physical scenario are almost the same. Both the physical scenario represents the same concept. Okay, now what we are going to do, we are going to consider a small portion on this bar. So let me localize my attention on the small portion. So I'm going to represent that by this red here. I'm going to consider the small portion on this bar. Okay, let me shade this, and let me say that I have considered the small portion at a distance, let us say that at a distance of x1 from the left extreme end. Let us say that the length of the small portion that I have considered is dx. Now my question here is, what is the rate of loading on this small portion? So I will repeat my question. What is the rate of loading? Maybe right at this place, right at the center maybe. So I'll use this eraser. What is the rate of loading at this small portion that we have considered? Maybe at the center. If you look through the lens of calculus, you have to find the rate of loading at the center. So what is the rate of loading on this small portion that we have considered? Simple. The rate of loading is q into x1. That is the rate of loading at this small portion. Now the next question here is, what is the load that is acting on this small portion? What is the load that is placed on? No, see, I have to use my words very, very, very carefully. What is the load that is placed? I'm not saying the load that is acting. All I'm saying is the load that is placed on the small portion. I'm not using the word acting. So there is a subtle difference. It is not the load that is acting on the small portion, but the load that is placed on the small portion. That is q into x1 into dx. Because if the rate of loading is q into x1 is the rate of loading, let us say that is the rate of loading for 1 meter, then for dx meter, what would be the rate of loading? So if you just cross multiply, the answer that you are going to get if you just cross multiply in order to get the unknown is q into x1 into dx. That is the load that is placed, that is located on the small portion. So we are very clear with our physical scenario. So that is the load that is placed on the small portion. Now what I'm going to do is I'm going to consider the next small portion. So I am going to consider the next small portion. So that is represented by this yellow here, and that next small portion is considered at a distance of x2 from the left extreme end, and the length of the small portion is dx. What is the load that is placed on the next small portion? That would be q into x2 into dx. Now what I'm going to do is I'm going to consider the next small portion that is represented by this white here, the next small portion that is considered at a distance of x3 from the left extreme end, and the length of this next small portion is also dx. The load that is placed on the next small portion is q into x3 into dx. And I'm going to consider the last portion, the load that is placed on this last portion. So that I'm representing that by this blue here, that is q into x4 into dx. x4 is the distance from the left extreme end to the blue portion that we have considered. Okay, q into x1 into dx is the load that is placed on this small portion here. q into x2 into dx is the load that is placed on the small portion here, so on and so forth. So you know the exact physical scenario of the mathematical equations. Now coming to the point here, coming to the red portion here, so everyone please localize again on this small red portion. So pay attention to this small portion. That is the portion that is under investigation. Now the question here is, you have to define the stress acting on the small portion, and you have to define the strain acting on the small portion. So let me take a new page. So here we go. Let me represent the stress that is acting on this small portion. So here is the beam. I'm sorry, the bar. And this red is the small portion that we have considered at a distance of x1. Okay, and I'm going to define the stress on the small portion. What is stress? Simply, it is load by area. Question here is, what is the load that is acting on this small region? I will tell you the answer. The load that is acting on the small portion is this load here plus this load here plus this load here plus this load here. That is the total load that is acting on this small portion. Now, why would I say that? Because if you take the physical scenario that we have considered here, okay, if this is the small red portion that we have considered, the total load that is acting on J is his own self weight plus the load of John plus the load of Peter plus the load of Peter. So the total load that is acting on J will be his own self weight plus the weight of John plus the weight of Peter. If you represent that physical scenario here, so the total load that is acting on this small portion is the weight of all the loads onto the right hand side. It is the weight of all the load that is acting on the right hand side, so weight of all the loads. So how do you find the weight of all the loads? I just told you the equation. The weight of all the loads is qx1 into dx plus qx2 into dx plus qx3 into dx plus qx4 into dx. Now let us say that this length here, now coming to this point, this length here is dx, and we have considered this length at a distance x1 from the left hand side. Now I want you to tell me what is the height of the small strip and the length of the small strip. That would be the area of the small strip. So what would be the area? It is q into x is the height, q into x1 is the height, and what is the length? It is dx. That is the small area. So if you want to find all the area, if the area of the next portion, that would be q into x2 into dx. The area of the next portion, I'm sorry about this. Okay. The area of the next portion, that would be q into x3 into dx, and the area of the next one, q into x4 into dx, so on and so forth. So if you want to find the total load that is acting on the small red portion, you have to integrate from the point x to the point L. Generally, you have to integrate from the point x to the L. So this summation, q into x1 into dx plus q into x2 into dx plus q into x3 into dx plus q into x4 into dx can be represented, can be nicely packaged as integration. Okay, so I'm going to represent that by the physical scenario. So here we go. Let me take a new page. Okay, the total load that is acting on the small red portion is q into x1 into dx plus q into x2 into dx plus q into x3 into dx, so on and so forth. So this can be nicely packaged as integral of q into x into dx over the limit x to L. So if this distance, the small portion, is considered at a distance of x in general, and this is x is equal to L, the total load that is acting on the right hand side, including its self weight, we have to integrate from x to L. Okay, so what is the integration? It would be q into, if you integrate x, you are going to get x squared over 2 over the limit x to L. So you substitute the limit, it is q over 2 into L square minus x squared. So that is the total load that is acting on the small portion. Now I can define the stress on the small portion. So go to the next page. Let me define the stress. Stress is load by area. We just computed the total load that is acting on the small portion. It is q over 2 into L squared minus x squared. There is a total load. Q over 2 into L squared minus x squared load. divided by area, so it is divided by A. This is the small portion that is under investigation. If this small portion, because of the load that is acting, let us say that this point here is getting displaced along the x direction by an amount u1, and this point here is getting displaced along the x direction by an amount u2, and if the length is dx, then strain is u1 difference u2, which is change in length, divided by original length is dx. Otherwise, I can simply write it as du by dx. That is the strain. So clearly, I have defined the stress acting on the small portion, which is here, and I have clearly defined the strain that is acting on the small portion, which is here. Having defined stress and strain, I can now relate them. The relationship is Young's modulus, which is stress divided by strain. So Young's modulus is equal to stress is q by 2 a into L square minus x square, and the strain is du by dx. Go ahead and mathematically just move the objects. Mathematics is just like moving objects. Mathematically move the object. Let us see what happens to this equation. Take the denominator and put them on the left hand side. So what you are going to get is 2ae into du by dx. So allow the concept to sink in. It is 2ae into du by dx is equal to, on the right hand side, you will be getting q into L square minus x square. So on the right hand side, it is going to be q into L square minus x square. Now what I'm going to do is I'm going to differentiate this equation once with respect to x. So you are going to get d squared u by dx squared is equal to q into differentiation of L squared. L is a constant. If you differentiate, it just disappears. So L squared minus x squared. If you differentiate this minus x squared, what you are going to get is minus 2x. So that's what you will be getting. So I can cancel this 2 and this 2, and I can bring the right hand side towards the left hand side. So the equation that you are going to get is ae into d squared u by dx squared plus q into x is equal to 0. That is the governing differential equation of a bar that is subjected to uniformly varying axial load. That is the governing differential equation. There is information that is stashed in this governing differential equation. In the next video, we are going to solve this governing differential equation in order to squeeze out that information. Okay, now let me define the boundary conditions. This is a bar that is subjected to uniformly varying axial load. Boundary conditions are quite axiomatic. It's quite straightforward. At x is equal to 0, what is the value of displacement? Obviously, it is going to be 0. That is the first boundary condition. So first boundary condition, u of 0 is equal to 0. Displacement at x is equal to 0 is going to be 0. What is the second boundary condition? What about the strain on the right extreme end? So pay your attention at the right extreme end of the bar here. The strain, which is du by dx, at the right extreme end, which is at x is equal to L, that is going to be 0. Why would that be 0? You come back to the physical scenario here. So the physical scenario. Okay, here we go, our guys. What about the feet of Peter? What about the foot? Will it experience any force at all? You see, Alex will experience all the person's weight, all the weights of the guys beneath him, including his self-weight. So we are clear about Alex. Jay will not experience the weight of Alex. However, he will experience his own self-weight as well as the weight of John and Peter. John will not experience the weight of Alex and Jay. However, he will experience his own self-weight as well as the weight of Peter. When it comes to Peter, Peter will definitely experience his self-weight. When it comes to his foot, the tip of his foot, that will experience no weight at all. If that is the case, then this bar at the right extreme end here, that should not experience any force at all. So if there is no force, then there is no strain. So du by dx at x is equal to L is going to be 0. That is the second boundary condition. In the next video, let us see how to solve this governing differential equation. That would be easy. Thank you all for your patience. Radiate hope and do amazing work. Thank you.